for the last 30 years has been directed toward questions more or less exclusively evoked by doing abnormal things with matter rather than by simply observing its normal behavior. And how is that? Well, it's many different things. But you see, these relations and Einstein's relation E equals mc squared, these give you another code of translation. And that code says that there is a relation between length and time on the one hand, and energy and momentum in the other. The time can be connected with an energy. A time can be connected with an energy by this, and with a mass by this relation. And a length can be connected with a mass by this relation. And what that means is that if you wish to study the finer structure in space or in time of matter, you will be led to use very high energy or very massive particles. That if you wish to study very massive particles, you will need a lot of energy. That if you want to explore smaller and smaller regions of space, you will have high energies to deal with. And this, of course, is the reason for the overwhelming importance of accelerators and cosmic rays in this aspect of the progress of physics. In all of this development of atomic mechanics, there has been a similar trait of conservatism and a similar use of the idea of analogy to that I mentioned in relativity. Things like this, limits on the accuracy with which you can define the position or momentum of particles, dualisms between waves and particles and so on, they sound very radical. But throughout, there has been both a principle and a success in saying that in all situations in which it's all right to use a picture of waves, the Maxwellian description of these waves or whatever one had in classical physics shan't be monkeyed with. It is right. Wherever it is right to use a Newtonian picture of an orbit, that orbit will be followed. It is only when, in some way or other, one has a situation where these ideas don't apply that one cannot use the formal laws. And it is true that all the laws of quantum theory are aesthetically and in symbols are very much like the classical laws that they supersede. This trait of conservatism, this use of analogy, is what has made atomic physics so rapidly a success. Now, it's a revolutionary business, and I'm not playing that down, but it's only revolutionary at one point, really. It's revolutionary only at this point about the duality of wave and particle. And it takes everything else, more or less as it finds it, and preserves it. And that has led to some really astonishing successes. The question then is what happens when you take this new machinery, the quantum theory, the wave-particle duality on the one hand, and relativity on the other, and look at some of the old questions about the electron itself. You think that you would like to understand the motion of electrons in external fields. You'd like to understand their behavior. You'd like to understand how they emit radiation and all the rest of it. And that is the electron theory, which has come to be a great success and of which I wanted to talk. There are two basic processes. They don't always occur, but given the right circumstances, they will occur. One of them is very familiar, and one of them is very, very unfamiliar. The familiar process is that by which an electron, if it is not moving uniformly, and this E just means this particle, if it is not moving uniformly, will give out some radiation, and I'll indicate the radiation by gamma for gamma ray. This is what happens to electrons in antennae when you get radio waves. It is what happens when electrons are stopped by the electric fields surrounding the nuclei in the target of an X-ray tube, and you get the X-rays from it. It is a very well-studied thing, and I just have to put in here that there is something to accelerate this or change its motion in order to give the gamma ray. This is different from the electrodynamics of 1900, only in that we know that these gamma rays have their corpuscular properties and some of the detailed rules for the rate at which this happens correspondingly change. The other process is really a new one. It's not new today, it's new when it was discovered. And it is typical of the wave character of electrons that it occurs. And that is that a gamma ray plus some kind of a field, and we might add the field here to make the acceleration of the electron, and here for the gamma ray to hit an electric field. This does something that was not anticipated. This produces two things, an electron and a positive electron, what is called a pair. These are identical except in the sign of their charge. The fact that the laws of physics should allow a positive electron is not new. That is true of classical physics as it is of the physics of this century. The fact that this will happen, this materialization process, is a pretty direct consequence of rather general things, of relativity, of the wave-particle duality of the quantum theory. I know of no description which satisfies the requirements that nothing travel faster than light, and which satisfies the rules of the quantum theory, and which has in it light and electrons, which doesn't make this process a necessary thing. It has not been proved that no such theory exists, because that's the kind of hard thing to prove. But I have never seen one, and it's been tried for a long time. Well, this was a theoretical prediction, which the theorists who made it were somewhat reluctant to believe until the positive electron was discovered. It was discovered in the cosmic rays by Anderson and immediately gave an immense stimulus to the electron theory. These two processes, as they occur in nature, give rise to one of the phenomena which Carlson studied with success and great interest. The cosmic rays are many things. They have a mysterious origin, and they are interesting for all sorts of reasons, but a very great part of their interest is that they are a wonderful source of radiation of high energy which may go up to 100,000 times or a million times energies now available in accelerators, and may go even higher than that. So that if a phenomenon depends on having a lot of energy available, the cosmic ray is a good place to look for it. And now you see, what happens is that if you have an electron, and it comes somewhere near the nucleus of an atom, then it will be accelerated, and in the course of that, it will give off a gamma ray. And then the electron will go on with a little less energy. But now if the gamma ray comes near the nucleus of another atom, it will make a pair, an electron and positron pair. And this one may come near another atom and give off another gamma ray. Well, Carlson, we worked on this a little, and there's this distance here isn't very long. On the average, it's about a quarter of an inch of lead, something like that, and only about a foot of water. Not very, very big distances are involved. And they found these things in the cosmic rays. In fact, they'd been there all along. One was shy about what they were. and they are really impressive. The very high energy ones spread in the air. There may be at one time 1 million of these things in one event. They may cover a part of a square mile in distance, building up this enormous multiplicative event which is called a cascade. And this is a kind of vivid demonstration of the elementary actions of the radiation by an electron of light and the conversion of light into electron pairs, one after the other in different events. Part of the importance of this finding of Carlson's was that one saw these in the cosmic rays and was sure that this was a largely correct theory. Carlson had worried a good deal about whether the quantum theory of electrons and radiation was correct at all, because in the cosmic rays there are many particles that don't do that at all. They just go straight along and they don't multiply at all, and they penetrate through lots of lead. And there are other particles that do quite different things. And so very grave doubt was cast on the correctness of these theoretical ideas. But our doubts were largely resolved, and have since been even more resolved, when we saw that there were things that behaved just this way, and really quantitatively just this way. One of the important points, then, is that because of that certitude, and because in the cosmic rays there were things that didn't behave this way, which didn't multiply, which didn't give cascades, one knew that there were other particles in the cosmic rays than the familiar ingredients of matter. And that started a search and a period of discovery which has been accelerating and been of a most extraordinary vigor in the last years, so that at the moment we have some 24 elementary particles, most of them radioactive and unstable, all of them transmuting one into the other when they collide, though not without some inhibitions. They all transmute into something, but they all don't into everything, and which appear to be taking us very close indeed to the elements of the subatomic world, to the actual atoms of which matter is made. That is one of the byproducts. Some of these objects, not electrons, are quite inert and are connected with electrons only by incredibly weak forces, so that transitions occur very slowly indeed. Most of them, on the other hand, have very strong interactions with each other, which make transitions occur rapidly and make their production and their destruction very common events. And there are forces in nature enormously weaker than electric forces, and there are forces very much stronger than electric forces. Electric forces and electron theory appear to occupy a sort of middle ground. Well, the success of the theory of the electron in basing itself on these elementary reactions and with a quantitative and relatively straightforward way of describing how often and under what conditions they happened, led to at least two attempts at an analogous theory. One was Fermi's theory to describe the radioactivity of nucleons. The simplest example, though it was not then an example, is that the neutron is radioactive. It produces a proton and an electron and another little object which is called a neutrino and is hard to find. And Fermi made the theory of this in exact analogy to the transition of an electron from one state to another emitting a gamma ray. He made the analogy, electron being accelerated and going from one state to another, and in the process a gamma ray appearing. And he said, instead of that, a neutron goes to a proton, and in the process an electron plus a neutrino appears. And he tried to make it, he actually made it formally very similar. It turned out that with rather minor modifications, this gives a very strong and helpful description of the phenomena of radioactivity, but has remained an indigestible question in its connection with most other problems in physics. And the Japanese physicist Yukawa made an even more daring and, as we'll see, not so totally successful analogy to electron theory. He said there are these strong forces which hold nuclear matter together, neutrons interacting with protons, neutrons with neutrons, and so on. They are very strong, they have very short range, and they involve very often, when momentum goes from one particle to the other, an exchange of charge between one particle and the other. He said, well, I know that if this were electrodynamics, the particle, there would be a field of force stretching from one electron to the other, and this would be the wave aspect of light quanta, which go from one to the other. The quanta that go from one nucleon to another, they may be charged, and that would account for this phenomenon of charge exchange. And if they were heavy, that would explain the fact that the nuclear forces don't act over a big distance but have a range, because he would just point to the formula I erased. He would say an object of mass m can last a time, has an energy mc squared, and can last a time certainly not greater than this, because that is the uncertainty relation, and it can go a distance certainly no greater than that. So that should give a relation between the range of the forces and the mass of the particles that are associated with the field. And he did say this, and he said a few more things. And some very great truth there has been in it, and it has occupied physicists for a long time. This analogy that Yukawa made between the forces between nucleons and these new particles, which are called mesons, and the forces between electrons and light. This two-way analogy trying to keep the thing formally as similar as possible. But before one can really get into that, we'd better say a few words about some of the things that have happened to electron theory. Because as at the turn of the century, it is not free of some contradictions. It was not free of some contradictions and some troubles. If an electron can emit gamma radiation, then when an electron is just standing around, it of course won't free that gamma radiation because there's no source for the energy. It's not accelerated or anything. But it will emit gamma radiation and then reabsorb it. And the time will just be about the reciprocal of the energy of the gamma ray. If a gamma ray can make pairs, it won't do so when it's just traveling through free space. There's nothing for it to hit. But part of the time it will exist in the form not of a gamma ray, but of a pair of electrons, electron and positron. Those electrons in turn will sometimes be accompanied by secondary gamma rays, and those gamma rays sometimes in turn by secondary pairs. This sounds terrible, but fortunately each step in the process is less and less probable, and by about a factor of 1,000, because the number which measures the relative probability of these various things in the sequence, E squared over HC, this number is about 1,000. And that means that it is only 1,000th as probable that you find two gamma rays around an electron as that you find one, and it's only 1,000th as probable that you find one as that you find none. Still, these complications have two kinds of consequences. One is that if you want to talk about the real world, you ought to talk about the electron with its family, all its gamma rays and pairs and all the rest, and ask what they do. And this turned out to be very important, since the family changes the properties of the electrons a little, changes its magnetic properties, changes the energy levels of the simplest systems, hydrogen, an electron in the field of a proton, positronium, the system made up of one positive and one negative electron, twice the size of the hydrogen atom, behaving very much like the hydrogen atom. These changes, which were discovered in the years after the war experimentally, and which are just a description of the altered character of the electron because of this business that goes on all the time. Similarly with light, and the properties of light itself in the free world, when it's all by itself, are of course not altered, but the properties of light in its interaction with the rest of, with matter, with charges. The properties of light which make it shake off pairs when two light quanta collide. Well, this is one reason for wanting to give a description of these interactions. And the changes are, of course, small because this number, the charge, is small. The other reason is the following. We had made electron theory for a long time, but we had always been rather careful not to make it too well. We had calculated how often something would happen, and we'd done it roughly. And then we had not made corrections for all these complications that I have just outlined. And the reason we didn't make corrections was that those corrections, though they had a small coefficient, the one on the blackboard, also had a large coefficient which was multiplied into it and which was in general infinite. It was infinite because although the effects of gamma rays on electrons and of electrons on gamma rays are small for any given gamma ray, if you go to gamma rays of infinitely high frequency, if you consider more and more violent more and more limited disturbances, these add up and accumulate to an infinite amount. And the discovery that was made about 5 years ago, more than that, 8 years ago, was a very, very beautiful one, really. That is that there are two kinds of phenomena. The kind of phenomena which depend in a sensitive way on the behavior of electrons and gamma rays for arbitrarily high frequency, arbitrarily small space-time phenomena, and those which are relatively insensitive. And the only two which depend on the high-frequency behavior, which is the behavior in the very small, very short-time region, are the charge of the electron and its mass. And those are the things that are infinitely affected by these phenomena, very much as in the classical theory of Lorentz. And physicists then said, good, we'll give up this attempt. We can't calculate the mass of the electron. It would be meaningless anyway in a theory in which there are no other particles, because it could only be its ratio to the mass of something else. We'd like to calculate the charge. We'd like to calculate that number 1 in 1,000, but we'll give that up too. These things we'll measure. And then everything else will be given by the theory in a finite way. So they said, and this is what is called the renormalization program. It has the double purpose of translating from a discussion of an electron with none of its cloud and company of gamma rays and electrons around it to the description of the electron as it really is, and similarly with a gamma ray. And at the same time of removing from the description those features, namely the mass and charge, which would come out infinite and which are nonsensical. Well, of course, the basic idea is that the electrodynamics cannot be the whole story. But if you try now to modify electrodynamics, and it's been done many times, many different ways, to say, well, for very small regions of space and time, things will be different. It's very hard to make such a modification, lacking any real knowledge of the physics of that region, which is even formally consistent with the requirements of good sense, of causality, of the existence of matter, the continued existence of matter, of complementarity, and the rest of it. Now, this theory, so modified, has been very successful. It is the theory which has made it possible to predict the levels of hydrogen, to a part in 10 billion, and to do very well with the spectrum of positronium, and to give a very accurate account of phenomena at ordinary energies. And the reason for it is that one can do the corrections for the additional electrons and gamma rays step by step, expanding always to take more and more complicated situations, and each one is much smaller than the one that came before, maybe 1,000 times, maybe only some 100 times smaller than the one that came before. At very, very high energies, this convergence is not so good anymore, and that's been known a long time. And people have had the curiosity, the morbidity to ask, well, suppose that I don't do this step by step. Suppose I try to do the whole thing, and I might like to do that, because if I could get rid of this expansion, I might even get some insight into the value of this constant. I could say how things would behave even if it were a large constant. And there a very odd thing has turned out. It has turned out that although for ordinary phenomena one can probably get things accurate to 1 part in 10 to the 50th or something like that, and at energies as high as the highest cosmic ray energies, one still is almost certainly making no appreciable mistake in the discussion of electrodynamic things, of electron theory. Nevertheless, if one tries to do it just a little bit better and get it exact, and get it so it holds at all energies, then the theory turns out to have no meaning whatever. In fact, it predicts something like this, that the electron should have another state, another configuration, with a mass which is negative and is enormously negative. Something like that. This is 500. And you might say, that sounds pretty bad, but it's not only that the mass is negative and very enormous, which would be very bothersome, it's that whenever this state occurs, it occurs in such a way that if something goes into that state, it increases the probability of things going into other states. So you're producing more and more electrons and more phenomena whenever you have a collision or whenever anything occurs. This is just another way of saying this is utter nonsense, and it's utter nonsense of the same kind that we ran into with the Lorentz theory and the Dirac modification of the Lorentz theory of an electron. One has pushed the theory too far. One has pushed it to the point where it is saying to us, I am not logically consistent. You have left out something, and that has made a hole in me which I show, although I can't say what belongs in the hole. Now, what belongs in the hole, of course, is all the rest of the world. It is those weak interactions which occur in beta decay. It is those strong interactions and those 24 different kinds of particles, which may someday be 40 or 30 or even an infinite number, which appear in the great laboratory of the cosmic rays. It is all the rest of physics, which is not very closely tied in, and which leaves electrodynamics and electron theory an almost perfect, but not a perfect subject. The analogies, especially Yukawa's analogy, have not fared so well. The reason is not because his quanta have a mass and his quanta have a charge. The primary reason is that his analog of this number here is not small at all, but very large. And therefore, in his situation, the nucleon is very often accompanied not by one meson, but by several. These things cannot be treated as corrections. And the fact that they cannot be summed, that one cannot treat them in any other way than as corrections, means that one doesn't have, in a strict sense, much of a theory at all. However, it has been possible, with a good deal of sophistication, to use this analogy, together with a good deal of experimental information, to coordinate those phenomena which occur for mesons of rather long energy and low energy, and those phenomena which have to do with internuclear forces at rather large distances, comparable with the meson Compton wavelength, comparable to the meson rest energy, phenomena of scattering, of production, and of nuclear interaction. And this is a first and very modest step in the beginnings of sorting out the new physics. These 24 particles, they are there, and as I say, there are perhaps more. They have very odd properties. They were wholly unexpected. The theory of Yukawa, which was supposed to tie together a few of them, certain mesons and the nucleons, would, if it were true, only cover a very small subsection of the field. It doesn't cover that except in a more and more limited area. This subsection is not separate from the rest of the field, as electron theory is for most things, and it is clear that we are in for one of the very difficult, probably very heroic, and at least thoroughly unpredictable revolutions in physical understanding and physical theory. One of the great times in physics lies ahead, and it is certainly something that will often make us remember how much we miss the guidance and the companionship that Carlson could have given us had he lived. Through all of this story, there has gone the theme of the use of analogy in building physical theory. The analogy between Newton's laws and the laws of relativity. The analogy between Newton's laws and the laws of atomic physics. The analogy between Maxwell's waves and the waves of quantum physics. The analogy between Fermi's theory of beta decay and the quantum theory of the electron, between Yukawa's theory of mesons and nuclear forces and the quantum theory of the electron. Over and over again, the use of formal analogies. This is not all there is to it. We are trying always to feel our way into something new and unexperienced. We take into it what we have, which is our own experience, in this case, of the physical world.